building on what we talked about in terms of rotations, we're going to look at a few related topics. They may not seem related at first, but they are all of a piece. We're going to apply what we know about motion to the case of an object that rolls. And then we're going to formalize our idea of torque and then talk about a new conserved quantity. Its total cannot change if there is no net torque acting. So there's no net force acting on a system. We know that its momentum is constant. And then that generalizes to rotations, that if there's no net torque acting on a system, then the angular momentum of the system will be constant. We have a couple images here, classic physics images, to illustrate some things you might not have noticed about rolling. So we're trying to catch up here with Fred Flintstone and the wheel. The shutter speed for this photograph is such that the spokes at the bottom are crisp, clear, and in focus. And as you go up around the wheel, eventually become a blur, right? And that only makes sense if these spokes up towards the top are moving faster than the spokes at the bottom, right? And doesn't that seem curious? In fact, that is what is going on. For rolling of this wheel to happen, it's not just that it's rotating in place, it's also translating simultaneously. And as we'll see, the point of contact between the wheel and the ground is instantaneously at rest. That shape we can see from the second image, where there are some lights on a wheel, and then as the camera shutter is kept open, you just have a streak of light. So the center of the wheel is just executing translation, going left to right across the screen. Nothing all that complicated about that. It seems to be moving at a nice uniform clip. This point on the edge of the wheel, look at the shape that it's taking. It's going down, coming to rest for an instant, reversing direction. Right? Then it's going to start to come down again, come to rest for a second, and reverse direction. For this wheel to roll, this point on the edge of the wheel is following a curve that's called a cycloid. And it is instantaneously at rest. The motion of that point on the wheel, if it's rolling, is to come to rest for an instant and then carry on. That is why the friction that matters for rolling, so the force that keeps the wheel in contact with the surface that it's rolling over, is static friction, not kinetic friction. If the wheel is skidding, sliding, then it's kinetic friction. But since for rolling without slipping, the surface of the wheel is instantaneously at rest with respect to the ground, it's static friction that's relevant. All right. Let's look at that. A couple of different points of view, frames of reference, if you will. So this idea of rolling is to have translation happening simultaneously with rotation. Your textbook refers to the condition as smooth rolling, meaning that the wheel advances forward one circumference of the wheel every rotational period of the wheel, right? So there's no extra gain. It doesn't go further than the circumference because it was like perhaps picked up and thrown for a little bit of it, right? And it doesn't advance less than a circumference of the wheel per rotation, because the in that case, you could imagine that the wheel were skidding in place part of the time. So it isn't um, advancing a full circumference of the wheel. If you have the smooth rolling condition, or like every other person under the sun refers to it as rolling without slipping. So that's the way you probably see it referred to outside of your textbook. The rolling without slipping condition means that the center of mass of the wheel is going to advance a circumference of the wheel every period. So the velocity of the center of mass is the angular speed of the wheel times the radius of the wheel. And the acceleration of the center of mass is going to be the angular acceleration of the wheel times the radius of the wheel. Okay. And then you also have another condition if you wanted that basically the position of the wheel is going to be related to the angular displacement in radians times the radius of the wheel. And so that's where all three of these relations are rooted. The idea that um, the arc length is going to equal like laying out the circumference of the wheel as you're going along. All right. Another way to view this is pictorially by adding vectors together. And this is, one of the really pleasing examples of adding vectors together that once it's all in your head, it all makes sense. So rotation, if I look at points on the outer edge of the wheel, I have a velocity vector that's going to be tangent to the wheel, and it corresponds to a length of omega times the radius of the wheel. So I have a whole bunch of vectors tangent to the wheel, and their length is all the same for the rotational motion. It's going to just be omega times r. In particular, just look at top, center, bottom. At this instant in time, due to rotation, the top of the wheel is moving to the right with v-com. The bottom of the wheel is moving to the left with a velocity minus v-com. And the center of the wheel, since r is 0 there, is not moving. All right. Now the entire wheel is translating forward. So every point on the wheel is moving to the right with a velocity v com, and we can add those vectors together. So obviously at the top of the wheel, v com plus v com both pointing to the right give me a velocity vector that is 2 v com pointing to the right. At the center of the wheel, 0 plus v com is going to give me v com to the right. And then at the bottom of the wheel, the point in contact with the ground, rotation gives me minus vcom, translation gives me plus vcom, and so the point of contact between the wheel and the ground is at rest instantaneously. Its velocity is 0. And then this confirms what we saw in that first picture. The top of the wheel literally is moving faster. The bottom of the wheel is at rest. You go off that point of contact, it's no longer at rest, but it's not moving as fast. Okay. Can also view this rolling as a pure rotation, but it has to be a rotation about a rotation axis that's moving. So that gets a little mind bendy to think about. It's not too bad. So that rolling as rotation plus translation, we can view that as a pure rotation about an instantaneous rotation axis that is the point of contact between the wheel and the ground. And so then to map out what the velocity field is for the rolling wheel, I just measure a distance, a position vector from the point of contact to the point where I want the velocity vector. The velocity vector is perpendicular to the position vector, and the length of the velocity vector is going to be equal to omega times the magnitude of this position vector. So the top of the wheel is moving fastest, and as I get closer to the rotation axis, it's going to be moving slower and slower and slower. And this point of contact between the wheel and the ground, just to emphasize again, it is instantaneously at rest. So it is a force of static friction that will prevent a wheel from skidding. If your tires spin out, it's because you lacked static friction. All right, let's try some questions. All right, circular hoop, so like a bicycle tire basically, rolls without slipping on a flat horizontal surface. Which one of the following is necessarily true? All points on the rim of the hoop have the same speed. All points on the rim of the hoop have the same velocity. Every point on the rim of the wheel has a different velocity. All points on the rim of the hoop have acceleration vectors that are tangent to the hoop. All points on the rim of the hoop have acceleration vectors that point toward the center. Which of those is correct statement? So the other four are false. One of them is a true statement. Read through them all, think through them all, argue it out, and then when you're ready to carry on, unpause the video. All right, the one that is true is that every point on the rim of the wheel has a different velocity. There will be 2 points on the rim of the wheel that have the same speed, but they'll have different directions. One is be directed up and the other is directed downwards. Same length, but different directions. So every point on the rim of the wheel has a different velocity. If it's rolling, they can't all have the same speed. They can't all have the same velocity. In fact, they all have different velocities, and you can pair them up. There will be 2 identical points that will have the same speed. All points in the rim of the hoop have acceleration vectors that are tangent to the hoop. None of them do. They're in pure rotation, so there is a centripetal force vector pointing in towards the point of contact between the wheel and the ground. So that is not a direction that's tangent to the hoop. And all points of the rim of the hoop have acceleration vectors that point towards the center of the hoop. Not true. Not if it's rolling. They're pointing towards the point of contact. And that's for the centripetal. They're changing speed. There's also a tangential component. All right. Little exercise, remembering what we know about rotational inertia. A bowling ball, so it's a solid sphere. You can neglect the holes and assume you don't have like some super duper mercury core bowling ball. Bowling ball is rolling without slipping at constant speed toward the pins on a lane. What percentage of the ball's total kinetic energy is translational kinetic energy? And then to knock down pins, you want this fraction to be as high as possible. Rotational kinetic energy doesn't do much to knock over pins. Translational kinetic energy, when the ball collides with pins, that does do work. It's going to move the pins. So we want the percentage of the ball's total kinetic energy in translation. For a bowling ball is at 50%, half, 71%, 46%, 29%, 33%. And don't just guess, try to work it out. It's not too bad. All right, and then the answer, 71%. See if we can get this to make sense for you. So the numerator, I want translational kinetic energy. So I'm going to have a half m v squared. And then in the, ooh, that was ugly. In the denominator, I've got total kinetic energy. So that's translation plus rotation. I'm going to have a half m v squared plus it's a half I omega squared, but I'm gonna start doing some shortcuts here. I'm gonna have a half for a solid sphere. It is 2/5 m r squared omega squared. And then rolling without slipping, our new good friend, or smooth rolling, is going to let a lot of this cancel out. So a half is in everything. Mass is in everything. That cancels out. And then v squared is the same as r squared, omega squared, rolling without slipping. So we have a half over, I'm sorry, we have 1 over 1 plus 2/5. So that's 1 over 7/5 is 5/7. Pretty high fraction in translational kinetic energy, which is exactly what you wanted for a bowling ball. And that is a bit above 70%. So there you go.